The last problem is a crane boom. In theory, it's absolutely no different than the parallel force problem, except we're going to have a variety of different lever arms where forces are not going to be perpendicular to the object. We're going to solve it the same way. The way I deal with these crane booms, first, let's draw the wall. I'm just going to redraw the picture a little. Here's the hinge. There's the boom arm. Okay, the goal is to draw all the forces acting on the boom. Let's go with the ones we know right away. Well, here's the load. 15,000 newtons. What else were we given? We were also told that the boom weighed 50,000 newtons and it's uniform. All of our booms are going to be uniform. We're not going to be dealing with non-uniform objects. So that means it goes directly dead center. Which means it's at a distance of L over 2. We have a rope. Let's draw it over here. And it has to point toward the wall. Ropes don't push on things. Let's call it T at 32 degrees at a distance of 1/3 of the length of the boom from that end. Now, you might think these are all the forces because it looks similar to the last problem. However, when there is a real actual hinge, we know there must be forces of the hinge on the boom and the boom on the hinge. They have to touch, they're touching, so they act on each other. Now, one of the questions is to find the magnitude of the force acting on the hinge. I can't find that directly. I'm not analyzing the hinge, I'm analyzing the boom. However, from Newton's third law, if I can find the force of the hinge on the boom, that's the same as the force of the boom on the hinge in terms of magnitude. So, that's one thing. The other thing is, I have no idea exactly which way the force of the hinge on the boom acts. I do know it's pointing roughly along the length of the boom, but I'm not going to draw it that way because I'm not 100% certain. But I do know it acts upward to the right, which would be the first quadrant. So, if we want to analyze, what do all of these forces have in common? They're all first quadrant forces. So, if I have an unknown force, because I don't know exactly which way the force of the pin acting on the boom is, I can take a look at all of those forces and realize one thing. All of them have this in common. They have an X or a horizontal component this way, and a Y or a vertical component this way. This is a way you can always replace an unknown force if you have a good idea which way it points. These are the horizontal and vertical components of the hinge. So this is what we're going to draw. H and V. They are the components of the hinge pin force. If I find those components, all I have to use is Pythagorean theorem to get the magnitude. I'm not going to worry about the angle. So if you look, what we have is an object with a bunch of forces on it. So we're going to do the same thing. We're going to sum the torques, but first we're going to find them. Torques are plus or minus force times lever arm. So what could you have? A torque due to H, a torque due to V, a torque due to the 50,000 Newton boom weight, a torque due to the 15,000 Newton load, or a torque due to the tension T. The torques due to H and V are 0. They're actually at the hinge. They also pass through the pivot, causing no torque. Why do we have them here? Well, in the torque equation, they cause no torques. But if we don't have them on the picture, we probably will forget they're there, and we won't be able to use them to find the actual force acting on the boom, the hinge force. So it's always good to have them in. We can make zeros. It's fine. Let's go through and find the torques due to all the other forces. Well, let's do the 50,000 Newton force. The force is 50,000 newtons. And I'm going to draw my little bar over there. Lever arm, perpendicular distance from pivot to line of action. Extend. Here you go. The lever arm is that length right there. We need that length. Well, look, that angle's 32. That angle's 32. That length, if you look at this triangle in terms of lever arms, once again, you need to know your triangles. That lever arm, hypotenuse, included angle, opposite side, adjacent side, L over 2 times the cosine of 32 degrees. Gotta look at the right angle to make sure we know. This is 32, adjacent, this is the side I want. Hypotenuse, included angle, adjacent side is cosine. So it's L over 2, cos 32. Make it rotate that way, negative. So we have a big, long, sloppy number. When you multiply it all out, you get negative 21201 newtons times L. Now, we'll keep the figs in and get rid of some of them later. Let's do the same thing for the 15,000 Newton force. Force, 15,000 newtons. Lever arm, extend. We need the perpendicular distance. Here it is. Look, just like we had over here. We just have a bigger triangle. The hypotenuse is L. So that lever arm is the adjacent side. L cos 32. Remember, it's just triangles. That force will make it spin that way. So it's negative. Negative 12721 newtons times L. Remember, we're just looking at triangles. Now we need the tension T. The force is T. We need the lever arm. We extend the force. It goes right up here. That's perpendicular. That's the lever arm. So we have a different triangle. Well, the hypotenuse from the pivot to here is 2/3 L. Included angle, opposite side is sine. So that lever arm right here is 2L over 3 times the sine of 32 degrees. And that will be positive because it'll make it rotate this way. Well, that is 0.353 times T times L. This was the hardest part of the problem. Now the easy part. Sum of the torques equals 0. Negative 21201 newtons L minus 12721 newtons L plus 0.353 TL equals 0. Look, we didn't know the length of the boom. It doesn't matter. The L's cancel. Now, when you are given a problem where you're not actually given a length, this should occur. If you were actually given the length of the boom in numbers, don't try to cancel those things out. You will actually have numbers. Really what this tells you is torques depend on the relative position of the force to the pivot point relative to all the other ones. Not, in other words, the boom could be a mile long or a meter long, you would get the same torque, in theory. In real life, it would be drastically different, but we're not going to talk about materials. This is good for us. Anyway, we can solve this for T. And when you do, you get a massive force of 96,100 newtons. There's the force. So now what do? If we want to find the horizontal and vertical components, we need some other equations. Like this. Sum fx equals 0. Sum fy equals 0. So let's look. We need some axes, x and y. And if you look, our x equation says h minus t equals 0. There's only two horizontal forces. So the horizontal component is 96,100 newtons. Let's look in the y. V minus 50,000 newtons minus 15,000 newtons. I'm running out of room. Sorry. Equals 0. V is 65,000 newtons. So what does that mean? To actually find the force on the hinge, what do we have? 96 100 newtons. 65,000 newtons. And this is the hinge force we're looking for. And when you use the Pythagorean theorem, you will get that force as 116,000 newtons. We're not really worried about the angle. So if this is the force of the pin or the hinge on the boom, the force of the boom on the hinge is the same. So what we ought to make sure is that a material is chosen to make sure that the hinge doesn't break. Because these are the major points of failure in our boom. It's the hinge or the tie cable. This type of force acting on the pin is called a shearing force. It generally acts at right angles to the length of the pin, and that's called a shear. So we'd want to choose a material and a thickness that could withstand a minimum of a 116,000 Newton shear.